Good afternoon, everybody. Welcome to the LCANZ Autumn Webinar Series and our penultimate webinar in the series. Great to have everybody here today. Hopefully people have been able to join, so we will get started. This is our penultimate webinar, so we do have one more next week, which is again on water footprinting and focusing on agricultural products. All of the webinars that we've had so far have been recorded and they're available to view on the website. So please do check those out. And don't forget to register for next week if you haven't already. Also a reminder that we are running a competition through this series where you're able to either win your own individual membership or student membership, or for corporates could win a free SME membership to gift to a supplier for next year. So in order to win, you will need to register and attend, and there will be a short quiz just to make sure that everyone's been paying attention. So we'll be sharing some information about that once we've had the final webinar. So hope you enjoy them in the meantime. Also, we would like to thank our LCANZ members because this whole series is made possible by our membership subscriptions, and because mostly it's members who are speaking and sharing their news and stories with you. So if you are not already a member and have found some benefit through this, please do consider joining us. We have very reasonable rates, and your membership now would cover you through to the end of May next year. With no further ado, I'm very delighted to welcome Brent Clothier as our speaker today. Brent is Principal Scientist with Plant and Food Research and is President of the Royal Society Aparangi, and has a long history of involvement in water-related aid and development projects. So, Brent, I will hand over to you. Thank you.
Kia ora tātou, ko Brent Clothier tōku ingoa. No kiwi fruit on this one. I decided to take a different tack near the end. I thought I'd talk about electricity, wine and dates, because it gives a breadth and quite a difference. And I'm going to take a hydrological approach, trying to put sort of some hydrology into a life cycle assessment framework. This is a tale of three papers. A paper that with my student Indika Harath and the water footprinting of hydroelectricity in New Zealand. And then also with Indika, the water footprinting of wine in both Marlborough and Gisborne. And then the last one, as you noted, I've been working in the Middle East, having a look at what is the water footprint of dates in the United Arab Emirates. So a range of considerations. Let's have a look at hydroelectricity in New Zealand. This is the breakdown in 2010. It's still about 56, 57% hydro, but we have gone up to 82% renewables because wind and geothermal's gone up and gas and coal have gone down. But I just want to talk about hydro, the water footprint of hydro. So we have a river, let's say over a century ago, the sliver of the Waitaki River flowing down from the Southern Alps out to the sea. A small sliver of water and a large part of the landscape around Benmore, Aviemore was actually vegetation. It was transpiring at ETC, crop evapotranspiration. And then a dam or a series of dams were built, and now that ETC is also placed by open water evaporation from the dam surface. And of course, the seepage, which we assume just goes out the bottom of the dam, the lake, into the river anyhow. So there's three ways you can compute a water footprint. You can say the consumptive water use on the right-hand side is simply the amount of water that evaporated from the surface of the retained water behind the dam, E0, divided by the power generated. Or we could think about it as net consumptive use. What is the difference between free water evaporation and crop evapotranspiration? And you could do it by net consumptive water use. Or you could do it the way that I would favour it is net water balance, because not only does the dam surface, the lake surface behind the dam evaporate water, it also captures rainfall. So let's have a look at that. And New Zealand's electricity is generated essentially in two regions around the Waikato, and you can see there. Let's have a look at Rotorua on the weather there. The rainfall far exceeds open water evaporation, ET0, and crop evapotranspiration, ETC. However, if we go down to the South Island around Benmore, you can see that rainfall is very low. Crop evapotranspiration is very low. It's a very arid landscape. And if you put a free water dam there, then the evaporation from that dam is very high. Similarly with Clyde, the open water evaporation is very high. Then, of course, if you go to Manapuri, there's a lot of rain there relative to what else is happening. So in the wet regions, you can see that the rainfall is 1.5 times the amount of water that is evaporating from the lake behind the dam. Whereas if we go to the dry regions, the rainfall, the precipitation is actually only about 1/3 of what is happening from the dam surface, the lake surface. So if we look down in the South Island, you can see, yes, there is a water footprint. I'm just going to focus on the water footprint 3, the net water balance. You can see that there is more water is lost from the dam in all except Manapuri. In Manapuri, the rainfall is greater than the free water evaporation. And if you look at the landscape around Benmore, you can see why that is. Those hills are brown, nothing much is happening, and suddenly you put free water there and you get a lot of evaporation. Now, in the Waikato, you can see, look at the landscape there, it's green. There's a lot of rainfall and all the numbers are negative because the dams are catching more water than would be evaporated. So the dams actually serve as a collector of rainfall. In fact, they have a negative water footprint because they capture more than they lose to the atmosphere. So when we do the calculation for these 3 different types, here in New Zealand, irrespective of the method you use, the consumptive, the net consumptive, or the net water balance, these are very small numbers from what have been proposed from overseas studies, and that's gigajoules is, of course, the unit of energy that is produced by those dams. So in summary, I think the water balance approach is hydrologically rational. That's what happens to the hydrology. Dams collect water and dams evaporate water, and look at the balance between that. And as I've said, in the Waikato and Manapuri, you can have negative footprints because rainfall simply exceeds evaporation and the receiving water resources are recharged. So I would advocate the use of that smaller number of 1.55. Nonetheless, is it reasonable to calculate a national average, which might hide local issues? Because hydrology is very local. Unlike, say, the carbon footprint of a product where we all share the atmosphere, catchments do not share water with each other. So water footprinting is very localized, related to the local hydrology of the catchment. So that's my assessment with Indika and others, and Ranveer was a co-supervisor with Indika on this in terms of calculating the water footprint of electricity. So when we go to have a look at agricultural products, we have to think about the colours of the water footprint. The green water, the rainfall that falls out of the sky and gets stored in the soil and transpired by the plant. I would also add, and it will become important as you'll see, not only is that water that falls on the land stored, if more falls on the land can be stored in the soil, it drains back down. Then there's blue water. If the green water runs out, then of course we go to lakes, rivers and aquifers to use it for irrigation, or even in the case of, say, wine, we might use it for frost protection. And then there's the grey water footprint. The soils leach, and so chemicals go out the bottom, and that could change the water quality of the receiving water underneath, and I'll talk a lot more about that right at the end. So this is what the water footprint network developed out of the Netherlands. You can see this is the direct and indirect, the green, the blue and the grey, and one is about consumption and one is about pollution. But look at that box on the other side, the return flows. And this is a point I want to stress. Hydrologically, it is not lost. it returns to the blue water resource. So that's why we have to consider net water use. Drainage out the bottom of the root zone recharges the underlying water resource. So it's not just about consumption. So the water footprint network considered blue and green. And when they gave their results to the Food and Agricultural Organization, you can see that they came up and said that one glass of wine takes 120 litres of water consumption. That's 720 litres per 750 ml bottle of wine. So that's a pretty large number, really. If you look at that, you'd probably want to drink beer. So if we go and have a look what Indica did, we took as a functional unit a 750 ml bottle of wine at the winery gate, and we had a look at the foreground and the background system, and had a look at what we were going to consider in terms of the water flows in there. We looked at vineyards, 36 wineries throughout New Zealand. We looked at vineyards that cover about 12,500 hectares, both in Marlborough and in Gisborne. And we used our soil plant atmosphere model called SPASMO to quantify the water use and drainage. And we used 40 years of actual weather data to drive that model. So if you look at rain-fed grapes, this is the water balance you would calculate. The green is the inflow and the outflow. There's no irrigation in here, so that's the green water use. And then if you've got irrigation, of course, you see, you're taking water. If you look on the right-hand side, you're taking water out of the blue water resource, whether that be the aquifer, as shown here, or a river or a lake. You can see that we have a blue water resource. Note the connectedness of the blue water resource with the drainage that flows back down through it and the runoff that will end up going into it as well. So it's important here, from my perspective, from a hydrological perspective, to see the net balance. So the key point here is that runoff and drainage recharges blue water and irrigation draws from it. So when we looked at vineyards across Marlborough, Marlborough has a Mediterranean climate. It's dry in summer, and when the vines have no leaves on in winter, there's rain, you can see that actually there is more water flowing back into the blue water resource than ever been taken out by irrigation. So that's the net usage of water. So when you do that calculation, you look at the hydrology of what Marlborough might look like, and it's very similar for the Waipoua River and Gisborne. You can see that in Marlborough, for every functional unit, a bottle of wine, you can see that under the vineyard, there's some 80 litres of water flows back to the aquifer. The winery takes 13. And that is consumptive use, and there's no return. So the net return is about 67 litres going back into the water resource. Of course, Gisborne's quite wet. And you can see there that under the vineyard, because of those rains, and of course over the last couple of months, there's been some massive rains that would make this a very large number. So there's about 400 litres of water going back into the aquifer under Gisborne vineyards, whereas the winery is only taking out about 13 or 14. The good thing is that this highlights the impact. You can do comparisons. It's quite easily to understand from a non-technical community. It rains in winter, it recharges the river. In terms of reporting, say through Sustainable Wine Growers New Zealand, you can track and trace. And also, and when you're looking at resource consents, it is consistent with how you might apply regulatory policy through the Resource Management Act. So every bottle of wine produced in Marlborough and Gisborne contributes on average 67 or 400 litres to the environment. So I would challenge the fact that no, it's not 720 litres per bottle in terms of net consumptive use, because we need to look at the overall balance. A bit of a change of tack here. We have been working since 2013 on a range of projects in the United Arab Emirates, which, unlike Gisborne, is hyper-arid, extremely dry, essentially zero rainfall. And we've conducted it under a government-to-government or G-to-G agreement between New Zealand and the government of the United Arab Emirates, and we've been working with Environment Agency Abu Dhabi, because you can see in that inset the level of the groundwater is dropping as they're consuming huge amounts of water, because essentially the groundwater there that is being used for irrigation is fossil water. It's not being recharged. There are no surface water resources. There are no connectedness. It essentially never rains. And furthermore, you can see the change in salinity. Some of the areas where there is agriculture, the water is becoming very saline. Agriculture consumes 75% of the groundwater. There's limited left, and you can see that dates are hugely important in Arab culture and the Islamic religion, and they consume 1/3 of all groundwater takes. So not surprisingly, Environment Agency Abu Dhabi had some substantial concerns around that. So we've been carrying out, we've completed 2 very large projects, and we're still carrying out one that I'll mention a bit more. And this project here on dates involved Ahmed El-Mawani, who, through my adjunct appointment to Massey, graduated with his PhD from Massey in 2020 on how much water dates use. And we had a look at that. So in terms of the green water footprint, it is pretty clear. The green water footprint is 0. There is no rain. And so when we calculate the blue water footprint, we were looking at 3 cultivars of dates, Lulu, Halas, and Shalar, irrigated with water of 2 different salinities. And the work we did there on the 2 different salinities of 5 decisiemens per metre or 15 decisiemens per metre is quite important. And of course, we had the yields and the irrigation usage from those, so we could get the date yield and the blue water footprint. So the blue water footprint is quite substantial. Yes, 650 litres to produce a kilogram of dates. So that's quite a large number when the blue water is a fossil resource that's not being recharged. Then we calculated the grey water footprint. And not surprisingly, because of the way that fertiliser is applied, there is a nitrate footprint due to the application of fertiliser and mulches. So that's about 520 litres. Per kilogram. But what is really spooky is when we calculated, when you're irrigating with saline water, the grey water footprint for salt is huge. It's nearly double the other 2 footprints. In other words, we're irrigating with saline water. The dates are taking out only fresh water. And so there is a massive amount of salt being pushed below the root zone because you have to over-irrigate to push that salt out. So the salt footprint is nearly 1,000 litres per kilogram of date. So that's a real concern, because not only is the groundwater shrinking, the salinity of the groundwater is increasing. So the grey water footprint is the largest one. So that led on to an assessment. There has been a development of not only solar-powered reverse osmosis desalination plants. Oh, by the way, all the water in the Emirates is desalinated from the ocean. But increasingly, farmers are using small-scale solar or electric reverse osmosis desalination plants to freshen up their saline groundwater to put on crops. So we had some information that was quite useful here, because we had the 2 levels of salinity, and we said, well, what say you use one of these solar-powered desalination plants and take the 15 decisiemen per metre groundwater and freshen it up to 5. That would cost you 275 dirhams. A dirham is about 40 cents New Zealand. It would cost you about 280 dirhams per tree. The beauty is that that fresher water will increase the date yield of those trees by nearly 40 kilograms per tree. So that's the benefit in terms of yield of using that desalination. And if you take the dates price of 10 dirhams per kilogram, that means that you get 387 dirhams per tree from increased yield, whereas you only spent 275 to desalinate the groundwater. So the benefit cost ratio is 1.4, which is absolutely marvelous. And so the problem is that these desalination plants themselves have a very large grey water footprint. What do you do with the reject brine that comes out the back end of the desalination plant? And that led on to the next project. So this is the third big project, and we're just 1 year into the PhD student for that now. And indeed, here you can see that there are now 1,500 inland desalination plants used for agriculture scattered across. You can see the Liwa oases, that arc in the bottom on the Saudi border, and also around Al Ain on the Omani border on the right-hand side. There's a lot of desalination plants being used to freshen up groundwater. So what we're doing in the PhD here is on the right-hand side, we take the saline groundwater, we desalinate it and use the high-quality desalinated water to irrigate high value vegetable crops and date crops. And we take the reject brine from the back of the desalination plant and grow fish in it. So we're growing tilapia in land-based aquaculture. And now we have the fish pooing in the water, which is good because now we have nutrients in the salty water. We can then take that salty water and use it to irrigate halophytic crops like quinoa, mustard, salicornia, which we can use as forage for camels, or we can use it for food for human consumption. And that's indeed what we're doing. We're focusing on salicornia, which I think is also known as sea asparagus. We have it in New Zealand, but we don't tend to eat it, but it's very pleasant to eat. And you can make a sort of like a potato chip out of it. So, but what about the salt buildup through this process? So here is Mansour El-Tamimi, who is our new PhD student, and there you can see the salicornia. We're growing the salicornia with the salty water out the back end of the desalination plant, and we're measuring underneath with flux meters to see the quality of the water that's going back to the aquifer, and we're looking at saline groundwater, reverse osmosis brine direct from the desalination plant, and aqua brine that comes from the fish farm. Mansour's already got an award from the Khalifa International Award for Agricultural Innovation, so that's really a good start for his PhD. And so, just to conclude, life cycle assessment is a powerful analytical tool, but I would also add that the law of conservation of mass, both in terms of water and also in terms of salt, is unbreakable. And so we do have to make sure that any life cycle assessment we do carry out acknowledges the law of conservation of mass. So thank you.
Absolutely fascinating. Really useful walkthrough. To be honest, particularly fascinating with the UAE and salt. It's not something I've ever really thought about before. So a whole new open area, and it must be incredibly satisfying to see that research actually being put into practical use and making changes, which is what we want research to do. But yeah, really awesome.
In the Emirates, we're very lucky because, just a quick aside, when oil was discovered on the Arabian Peninsula, basically, and I don't mean this is a statement of fact, that they were basically desert Arabs or fisher people. And so a lot of expats flooded in. So in the Emirates, you have 9 million people, but you only have 1 million Arab Emiratis. And so now there's a huge push with their highly qualified education system to build up Emiratization, build up Emirati capacity. So to have 2 PhDs completed through Massey and a third underway is a huge benefit for them and for us in terms of G to G love it, because we're using our education system to tick a huge number of boxes in the Emirates.
Wonderful. I wanted to pick up a couple of questions from the wine study that I was curious about. So the first one, you mentioned that over the course of the year in the Marlborough region that there's more rainfall than there is water being used. Does the time of year then matter? Like because during the summer months it's dry and presumably that's when they're using the most water. How much impact did that have?
Yeah, that's sort of you've picked the sort of the flaw in my argument there a bit.
Sorry.
No, because although there's a net recharge of that water in winter, a lot of it may well flow into the Wairau River and flow out to sea. So it's not a utilizable resource. But I think what we will see, and we're seeing it now in Northland, for example, is where rather than sort of build massive dams, I'm not a great fan of dams, by the way, rather than build massive dams, as we're doing in in Northland and possibly increasingly in Marlborough, we will build detention storage to take that winter excess of water and store it so that it can then be used back in summer to offset that difference. So that's a very good point. So yes, the net balance is annual, and that doesn't necessarily help you when you're in the depths of a drought in February when all that excess water had flowed out to the sea in July, August. So, but it does give us the opportunity to think about how we might capture that excess for future use later on. Yeah, good point.
That makes a lot of sense, and I think also touches on. I was then going to ask, because that negative water footprint is essentially because of the rain. There's more rainwater than is being used, but the rain would be falling anyway. It's not falling because we're growing wine crops, right?
Yeah. Okay. Can I just quickly answer before you go on there? Yes, but guess what? In California, you don't get that rain. So that's the difference between a New Zealand vineyard and a vineyard in the Barossa Valley and a vineyard in California. We have that luxury of winter rain. Yeah. Other regions do not.
Yeah. Excellent. That makes sense. Thank you. So I'm going to stop hogging the limelight because there are a couple of other questions that have come in. Kim McGrowther, has asked, how standardized is water footprinting around the world now? And you clearly have experience around the world.
I think in a colloquial sense, it's a moving feast. There is our approach, there's the water footprint network approach, and there's the LCA approach. So we are trying to work out, my view is, how can we weave those together to take the strength of all three systems so that the woven rope out of LCA, water footprint network, accounting on consumption, and a full hydrological assessment makes some sense. So yeah, I think this is, I think in terms of LCA, there was you can go back to the past 2050, we're sort of talking decades, if I got it right, and whereas water footprinting has come in a little bit later, and we're still trying to work out, I know there's an ISO protocol on it, but we're still trying to work things out a bit.
Yeah, I certainly agree from the LCA point of view. Yes, there's been more standardization, but it's still young, shall we say.
And it just goes back to that challenge I highlighted. If we emit CO2 or greenhouse gas in New Zealand, it hurts the global atmosphere. If we consume water somewhere, it doesn't affect anybody in California. So the local, and I know the LCA approach is trying to build that in, and that's where we're saying is they're trying to build it in through hydrological consideration. So that's good. Yeah,
absolutely. Wonderful. And AJ's just asked, consolidated approach would be great. What would the barriers be to that consolidation?
Well, it's to use the oft-used word, it requires a transdisciplinary approach. You've got me saying, I'll go along with anything that obeys conservation of mass. And they're saying, well, how does that fit within an LCA framework? And that's the discussion we have to have.
Yeah. So Shreyasi asked, you mentioned that the water footprint method focuses on blue and green water, and what about grey water, and where does that fit in? And as we saw in the UAE, it was extremely important.
Yes, thanks, Shreyasi. Well, if you think of some of the water issues in New Zealand, one of the most difficult issues we're facing around agriculture in terms of resource consenting is around our nitrates. So nitrate is a substantial issue here. Salt's a huge issue. So the water footprint network approach is to take the biggest one. And I sort of did that here. And I said, look, the blue water's large. The nitrate grey water's large, but let's focus on the salt, which is the largest. But that doesn't get rid of the other problems you had. The blue water is still a very large number and the groundwater is running out. So you just can't say, oh, I'm going to fix up the grey water and everything else will be tickety-boo. It won't, because you've still got blue water issues. Green water is somewhat more passive because there's not much you can do about it, really. But except, as I say, you can capture some of it for detention storages.
Sarah, I think this is more of a comment than a question.
I see that.
But,
yes, No, I agree, Sarah.
I'll read it out, shall I, so that everyone can appreciate it. So the recent FAO LEAP report recommended using 2 different methods to assess the water footprint in a study, recognising the strengths of different approaches. And yes, agree.
Right.
And I guess that's probably the first and possibly most important step we can take to starting to bring that together so that these different approaches are recognised.
Well, that's what I sort of go back to. If we weave those 2 approaches together, the rope's going to be stronger for having both of them woven.
Wonderful. I think that might be a good place to finish. And those of you who are intent on using water footprinting, and I hope you are, use them both and come back and ask the experts for help if you need it, because it's been fascinating. Thank you, Brent, to hear more about those studies. Really appreciate your time. And just to repeat, we have one last webinar next week where Ranveer will be talking about water footprinting of agricultural products. So again, more focus on water and on the details. So I think AJ's just shared the link for registration. You can also register via the website. So don't miss our last one, especially if you want to win your membership for next year, because you need to be there to be in for it. And also to thank our LCANZ members again for your support, and to urge those of you who are here who are not members to consider joining us. We'll see you all next week. Thanks again, Brent. Bye, everyone.